IM1 students, happy Monday. Today's learning target is the beginning of Module 3, Topic 2. And so I can write equations and solve exponential growth and exponential decay problems. Our agenda today is first we're going to review and practice how do we write a percentage as a decimal from your grade school math days. Then we'll have our main lesson on how to write the exponential function equation. Given a scenario that's either for growth or for decay, or it's decreasing, getting smaller. And then we'll practice writing some equations at the very end of the lesson. So let's begin here. So decimal percent conversion chart. So if we have the decimal to go to the percent, we go from left to right, we multiply by 100. In order to go from a percent back to a decimal, we do the inverse process of that. We divide by 100. So let's start with the decimal, 0.75. So if you multiply by 100, we know that the decimal moves 2 to the right. So we just go 1, 2. There's my new decimal place. That's how we got the 75%. Go the other way, from 80, where's the decimal at? That's right. It's right there after the 0. You don't see it, but we know it's after the 0. So we move, when we divide by 100, we're going to move 2 to the left. So 1, 2. There's our new decimal place. So 0.8 represents 80%. How about if I did the 6%? Well, the decimals here, I move 1. Uh-oh, I need another 0. A placeholder, move another spot. So that's how we get 0.06 for 6%. You got to be careful. People make mistakes all the time on that. They put 0.6 for 6%. That's 60%. It's a big difference. 60% and 6%, big difference. All right, so we're going to practice some of these to get this down. All right, I want you to write 71% as a decimal. Go ahead and enter it now. I hope you got 0.71. 71%, the decimal's after the 1. We don't say 71.0%, so we move it 2 to the left, so we get 0.71. Be careful with this one, 5%. Can you write that as a decimal? So on this one, I put a leading 0 in front of the 5. My decimal's after the 5. So 1, 2 to the left, so I have 0.05. You should have 0.05 represents 5%. Okay, can you handle 19.375%? How do you write that as a decimal? Okay, let's take the decimal. We're going to move 2 to the left because we're dividing by 100. So we get 0.19375 is the decimal that represents 19.375%. Careful on this one, 0.27%. 0.27%, what decimal is that? I hope you got 0.0027 is the decimal that represents 0.27%. Ooh, big one here, 153%. How do you write that as a decimal? 153%. So for 153%, the decimal's after the 3. So we move that 2 to the left, so we get 1.53. Makes sense. 1 represents 100%. So 153% is 1.53. Last one, right, 0.00026% as a decimal. All right, on this one, you should have got the decimal 0.0000026. So decimal of 5 zeros, then 26. That's your decimal. All right, we're going to use this today. That's why I wanted to review this. I'd like you to write this down in your gold notes. Our topic is using exponential equations. We're looking at exponential growth here. So our model is going to be g of x equals a times 1 plus r to the x. So the r represents the growth rate as a decimal. That's why I just had you practice rewriting percentages as decimals, because the r is going to be that decimal that we were writing. So if I say it's 10% growth, it's going to be 0.1 or 0.10. If we say it's 25% growth, then R is going to be 0.25. 3.25. Okay, so when I rewrite the percentage as a decimal, that's going to be our R. And so we've been working with the last 2 weeks, f of x equals a times b to the x. So the b, the base, is actually going to be this 1 plus r when it's growing. You take 1, which is 100%, and the growth rate. So we add those together, that'll become our new base. So everything else is the same that we've been doing for the last 2 weeks. The only difference is how we calculate the b. It's going to be always 1 plus r. The a is still the initial value. That's our y-intercept on the graph, and that's our initial value. The x is going to be the time period. Now this can change. The time period, it can be days, it could be weeks, it could be months, it could be years, it could be hours, it could be seconds. So your growth is going to be in the scenario that we give you. You're going to figure out what the time period is. What's the time period for each growth period, okay? And you'll see that as we go through some examples. So this is the form we want to use. It doesn't have to be g of x. It could be f of x. It could be h of x, whatever you want to call the function. We could also just use y. So we could also write y equals a times 1 plus r to the x as well. Okay, let's look at an example. All right, John invests $10,000 in a savings account that earns 3.25% annual compounding interest. Write an equation to determine how much money he will have in an account after 8 years. So compounding interest is the idea. What's the interest period? So after 1 year, your money grows. Boom, that's your new amount. Then the next year it grows and it has that interest rate. Boom, there's your next amount. So you keep making interest off the original. So let's say, real easy number, 10%. Let's say you had 10%, put $100 in the bank. After 1 year, you'd have $110. Then the next year, you make 10% interest on that 110 versus the 100. So that next year, you make $11 interest. So now you're up to $121 in savings. Then the next year, you make 10% interest again, but it's on the $121, not on the original 100. You're making it on the $121. So you're making money off the interest as well that you had made before. So it gets bigger and bigger and bigger each and every year. That's why we have that exponential growth that you'll see. All right, so on this problem, what is R? Yeah, it's 3.25%, but do we write it that way? How are we going to write R in this problem? So R is the 0.0325. Again, what we just did for warm-up for practice, we took that 3.25%, we divide by 100, so we move the decimal 2 to the left, and that's how we get the 0.0325. Now tell me, what is the A value in this problem? So A is our initial investment, so we invested $10,000 in the savings account, so A is 10,000. All right, write the equation to determine how much money you'll have in the account after 8 years. Let's just write the equation without the 8 years, just with the X for the years right now. What would be the equation? When we write the equation, we should get g of x equals 10,000 times 1.0325 to the x power. Do you see the difference here in our base? Our base is 1.0325 because I went 1 plus r. So 1 plus 0.0325 is how we got 1.0325 to the x power. So now if I was going to evaluate this function for after 8 years, that means x is 8. So I'm going to go ahead and do that right now. If you have a calculator, see if you can calculate what's the value going to be after 8 years. So on my calculator, I went 10,000 times 1.0325 to the 8th power. So if you're doing on not a graphing calculator, just a manual calculator, you have to go 1.0325, the caret key to the 8th power, get that number, and then multiply by 10,000. And when you do that, you get $12,916. So after 8 years of savings, your original $10,000 is now worth $12,916. All right, let's look at another example. Let's use a current model here. Let's look at COVID cases in Placer County, our county here where Oakmont's at. We had 7 confirmed cases on our last day of class together. So that was on March 13th. There were 7 confirmed cases in Placer County. As of Friday, April 24th, which is 42 days later, we have 139 confirmed cases of COVID-19 in Placer County. So I kind of looked at that number and kind of figured out what's the average daily growth rate for that, and came up about 7.75%. So let's just say that's what our average has been, but we made some changes, right? So we've trying to do what you hear them say, flatten the curve. They want to flatten that exponential growth curve, right? That's what we're trying to flatten. We don't want this exponential growth curve taking off, and away. So we made adjustments, right? We don't come to class together anymore. We were very careful if we go outside of our houses, all that good stuff. So that's 7.75%. That includes all this work we've done to flatten the curve, if you will. So let's just make a ballpark guess here. I have no clue. This is not my area of expertise. But let's just say the average would have been 20% growth per day if we did nothing. We just came to class every day. We're still running business as usual. How many cases would we have had 42 days later in Placer County alone? So let's write the equation. Why don't you see if you can write the equation for that? So our initial value is going to be the 7 cases that we started off with on March 13th. And our growth rate is 20%. Our time period is days per day. Write that function. So to write that function, you get g of x equals 7, the initial value, 7 cases in Placer County, times 1.2 or 1.20 to the x power. So there's our function. So now let's see how many more cases we would have. Let's use 42 days. So let's make x be 42. Use your calculator. How many cases will we have had with the model I just made up? Again, I don't have any expertise in this area, but let's just say it was 20% growth per day if we did nothing. How many would we have had? So g of x or g of 42, I should say, equals 7 times 1.2 to the 42nd power. So the number I ended up getting with that is 14,815 people. So in the model I made up here, saying that our growth would have been bigger than the average rate we've had for the 42 days in the real situation, it's been a lot more people, right? You see that exponential growth, it just takes off. Then I don't even know if my model's too aggressive or my model's maybe even too light. We don't know. This is the reason why we're doing our classes this way, right? We're flattening that curve. So keep doing a good job with that. So exponential decay. This is going to be really the same idea, but this time I want you to notice the base. It's going to be 1 minus r. See this? 1 minus the rate. So you'll get a problem that says, oh, things are decreasing, 20% per year. Well, then you go 1 minus 0.20, which is 0.8. Or it says it's decreasing 33% per year. All right, 1 minus 0.33 is 0.67. So our base would be 0.67. Remember, when we have the a value is a positive number and the base is between 0 and 1, we have that curve that is decreasing. When we have a value is positive and we have a b value that's greater than 1, then we have the exponential curve that is increasing as you go left to right. So this is going to get for decay. This always will give us a decreasing curve because we're going to start with some kind of positive number for the initial value, and we're multiplying it by a number less than 1. So it's getting smaller and smaller and smaller. All right, let's look at an example. The population of downtown is currently 50,000 people and is declining at a rate of 7% per year. The city planners want to determine what the population will be in 10 years from now. Write an equation and solve this problem. Okay, so what does the 50,000 represent? 50,000. That's right. The 50,000 represents our initial value. That's the A. So A equals 50,000. What is R in this case? 7%. How do you write that as a decimal? R equals 0.07. Right? You move that decimal 2 to the left. You got to put in a 0 as a placeholder. So 0.07 is R. So what's the base actually going to end up being? What does 1 minus 0.07 become? That's right. It's going to become 0.93. So we know that this is going to be 0.93 is ultimately what's inside those parentheses there. That's our base. If it's the old f of x equals a times b to the x, our b is 0.93 for this scenario. So let's write the equation. G of x equals 50,000 multiplied by 0.93 to the x. X represents the number of years. So then if we want to solve this for 10 years from now, we say G of 10 equals 50,000 times 0.93 to the 10th power. Then we're going to use our calculator. So when I used my calculator, I came up with 24,199 people. So population will be roughly half of what it started off with at the current level. If you're not sure on how to use Desmos for this or how to do it on a calculator, I will be showing that to you another day. Today, I want you to understand how to write the equation is the main bread and butter of today's lesson. Okay, if you can already find the answer, then great, you're ahead of the game. Okay, all right, one more example. So I was looking at the data for the United States and the number of COVID-19 cases, how many new cases are reported each day or confirmed each day. And with hopeful thinking, I'm wishful thinking right now, I'm hoping the peak number was 11,571 new cases on April 15th. From there, the data has been going down as terms of number of new cases each day, number of new cases. So let's put in our model, let's say that was our peak, and now we are decreasing the rest of the way from April 15th. So let's put in our model. Again, I'm not an expert in this. I have no clue. I'm just making up numbers here for fun. But let's say our decreasing at a daily rate of, let's say, 12% moving forward. If we decrease 12% on average moving forward, what would that look like? And can we use that model to predict how many new cases we would be getting 30 days from April 15th, 60 days from April 15th, and so on. So see if you can come up with what's A, what's R, what's that going to give us to become our base, write that equation. So our initial value would be the number of new cases that we got on April 15th. So that's 11,571. That's our initial value. Our rate, we say we're hoping it's going to decrease 12% per day moving forward. So 12% is 0.12. So to get the base, if you will, we're going to go 1 minus 0.12. That's how I got the 0.88. So, and then to the x, which is going to be, in this case, is number of days. So now if we want to solve this for 30 days or 60 days or whatever, we just substitute x with that number. So I'm going to do it on the calculator for 30 days, and then I'll do it for 60 days. You want to try it? See if you can get, what would it be after 30 days? All right, so for 30 days with this model that I created here, we would be down to just 250 new cases in the United States. So that would say from April 15th, so about mid-May, we'd only be getting 250 new cases a day. And if you go out to 60 days with this model, you'd only be getting 5 new cases a day in the entire United States, 60 days out. Okay, again, I know nothing about this stuff. My numbers are just for kind of for fun here to show you a model example of decay with very positive thoughts that we are going to be crushing this virus and seeing a nice trend downward. So this is just an example of a model. Actually, in real life, the model doesn't work nice, perfect exponential curve. It's bouncing up and down and going all over places, but there's a trend over the long haul that does fit an exponential model. Kind of similar to what we were doing with linear regression. This would be similar, would be regression with an exponential function. All right, let's see if you can write a couple equations, and then we'll call it a day. A town with a population of 5,000 grows 3% per year. Find the population at the end of 10 years. So write the function equation and set it up for it to be evaluated. You don't have to solve it unless you know how to do that on your calculator. So on this one, I hope you f of x equals 5,000 times 1.03 to the x. You could have wrote a different function name. You could also said y equals that. And so then if I evaluate that, f of 10 equals 5,000 times 1.03 to the 10th power, I end up getting 6,720. Let me make note, officially on my calculator, I actually got 6,719.6. But we're talking about people, so we're going to round to the next whole number. So it's very with the word problems that you're given, it kind of tells you how you do the rounding. So if you're talking about people, you're going to round it to the nearest person. You're talking about money, you're probably going to round either to the nearest whole dollar, or sometimes you want to maybe round to the nearest cent. So you go 2 decimal places out. So it's based on the problem. Amy makes an initial investment of $5,000. The investment loses 13.5% each year. Find an amount Amy has at the end of 8 years. Yes, students, when you make investments, they don't always turn into winners. I've made a number of investments. My wife and I have made a number of investments that have been losers. We've lost money on them. But over the long haul, if you have a lot of different baskets that you make your investments in, hopefully overall you're doing well and your money's growing over time. But you never want to put all your eggs in one basket if you need that money. If you have some risky money, then fine. But if you have money that you want to count on and growing it, then you want to diversify. So anyway, this is an example of losing money. You're losing 13.5% per year. And how much does she have left after 8 years? So write the equation for me at least. And bonus is, can you come up with a number? So the equation is f of x equals 5,000 times 0.865 to the x. How do we get the 0.865? 13.5% is 0.135. So we went 1 minus 0.135. That's how we got the 0.865. So then put that in your calculator, and we end up getting $1,567.10 is what she has left in her investment of $5,000 after 8 years, losing 13.5% a year. Suppose you deposit $1,000 in a college fund that pays 7.2% interest, compounded annually, so our time period is every year it grows. Find the account balance after 5 years. So see if you can write that equation. Think to yourself, is this growth or decay? Our equation on this one is f of x equals 1,000 times 1.072 to the x power. So this is growth. We're saving money and we're earning interest, so our money's growing. So it's 1 plus the rate. The rate is 0.072. So it was 1 plus that, which got us the 1.072. All right, and then if you use your calculator on that one, you end up getting $1,415.70 after 5 years. That's what your $1,000 has turned into. Last one. Radioactive element decays at a rate of 5% annually. there are 40 grams of the substance present. So we have 40 grams of this radioactive material. How much of the substance remains after 30 years? And they want us to round to the nearest tenth. So can you write the equation for that? And bonus, can you figure out how much is left? So on this one, you should have had the equation f of x equals 40. The initial value is 40 grams times 0.95 to the x. Where it's decreasing, it's decaying, it's decreasing, getting smaller. So we went 1 minus the rate. R was 5%, which is 0.05. So we got the 0.95 by going 1 minus 0.05. That's how we get the 0.95. So that comes out to be about 8.6 grams of the radioactive material still with us 30 years later. All right? It decays, it gets less and less, but there's still a lot with us after 30 years. Will this ever go to zero officially? Will it ever go to zero? The answer is no, because you keep taking, you get 5% less, 5% less, 5% less, but 5% less of something is still something. You still have something left over. So it gets so small where it basically becomes as close as you can get to zero as possible, but officially it never actually officially touches zero. All right, I think we had a good day. Tomorrow we're going to continue with this process. So again, this is our first day of this. If this was a little stressful for you today, we're going to do more mastery over time. Okay? Have a great day, great evening, great night.